Welcome to MS Exam Lab and to the DP-800 series, Developing AI-Enabled Database Solutions. This is Episode 1, our first case study, Contoso and its Fleet Intelligence Platform. Because this is a case study, we'll do it the way the real exam does: read the entire scenario first, the existing environment, the plan changes, and every requirement, and only then work through the 9 questions one at a time with a full explanation for each. Every answer is verified against Microsoft Learn. Let's begin. First, the existing environment. Contoso has an Azure subscription in North Europe. The estate currently runs Microsoft SQL Server 2017, and it's being modernized to SQL Server 2025 and Azure SQL. The customer feedback table has a FeedbackJson column that stores JSON feedback documents, and it carries a full text index. Remember that detail, it matters later. The orders table has roughly 120 million rows. Customer ID is highly selective, and order date is used for range filtering and sorting. The vehicle incident reports table holds weather, traffic, and location details written as free text, and analysts say it's hard to find similar incidents. The ingestion pipeline sometimes fails for 2 reasons: malformed JSON and duplicate payloads. And a fleet dashboard query runs slowly. Its execution plan shows a clustered index scan, which is our clue that an index is missing. Next, the plan changes and the AI workloads. Contoso wants to modernize the Fleet Intelligence Platform to support AI-powered semantic search over incident reports. The AI workloads are 3: vector search, modernized API access, and retrieval augmented generation (RAG) pipelines. For AI search and embeddings, the requirements are specific. Embeddings must be stored in dedicated Azure SQL database tables. Embeddings must be generated from rich natural language fields. Chunking must preserve semantic coherence. And hybrid search must combine 2 things: vector similarity and keyword filtering or boosting. Keep that phrase in mind: rich natural language fields. It decides one of our questions. Finally, the remaining requirements. Security. Support staff must be restricted from viewing personally identifiable information. For example, full email, and Contoso will use row-level security and masking to do it. Maintenance events. Any change to a row must update the last modified UTC column to the time of the change, and it must avoid recursive updates. Development. The team uses Visual Studio Code and GitHub Copilot and must retrieve live metadata from the databases. And for the FeedbackJson column, 4 things. Extract the customer feedback text from the JSON document. Filter rows where the JSON text contains a keyword. Calculate a fuzzy similarity score between the feedback text and a known issue description, and order the results by that similarity score highest first. That is the complete case study. Now let's answer the questions. Question 1. This maps directly to the FeedbackJson requirements we just read. You need to complete the T-SQL query. Project the feedback text, filter rows whose JSON text contains a keyword, and order by fuzzy similarity highest first over a column that has a full text index. On screen, there are 3 blanks: the projected column, the where filter, and the order by key. Read the query and decide each. You have 10 seconds. Let's take the blanks in order. Blank 1 is JSON value of $.text, aliased as feedback text. JSON value extracts a scalar from a JSON document, and $.text is a single string, so JSON value is exactly right. The trap here is JSON query, which returns an object or an array. Ask it for a scalar path and it returns null, so your feedback text would come back empty. Blank 2, the where filter contains a feedback JSON and the keyword. The requirement is literally filter rows where the JSON text contains a keyword, and the column has a full text index. That pairing is the classic case for the contains predicate, which uses that full text index for a fast keyword lookup. Now, why not edit distance similarity in the where? Blank 3, the fuzzy score is already computed in the select as similarity score, so we order by similarity score descending to bring the closest matches to the top. Ordering by the text or the keyword wouldn't rank by closeness. Question 2, a yes or no hotspot. The vehicle telemetry table is system versioned, a temporal table, and it has a JSON index that covers 3 properties: latitude, longitude, and accuracy. Decide yes or no for 3 statements. 1. The data is stored in a partitioned table. 2. It meets the JSON property querying requirement. And 3. A filter on the heading property will use the JSON index. You have 10 seconds. The answers are no, yes, no, and each one turns on a precise detail. Statement 1 is no. Being able to keep history is not the same as being partitioned. The table defines a period for system time, which makes it a system version temporal table, but there is no partition function and no partition scheme anywhere in the definition. Temporal and partitioned are 2 independent features, so stored in a partition table is not met. Statement 2 is yes. The requirement is that latitude, longitude, and accuracy be filtered by an index seek, and the JSON index is built on exactly those 3 paths, so a seek on any of them is index-backed. Statement 3 is no, and this is the subtle one. An index only contains the paths it was built on here: latitude, longitude, accuracy. Heading was never added, so a filter on heading has no index to seek and falls back to a scan. The index name looking right is irrelevant. What matters is whether the specific path is inside it and heading is not. Question 3, another yes or no hotspot on the security requirement. The customer profiles table uses dynamic data masking on name, email, and phone, plus a row-level security filter policy by region. Support staff never hold the unmask permission. Decide yes or no. 1. This meets the PII security requirement. 2. Admins can see all rows through an application. And 3. Masking still applies when row-level security filters rows. You have 10 seconds. The answers are yes, no, yes. Statement 1 is yes. Dynamic data masking is applied to the name, email, and phone columns, and the requirement says support staff never hold the unmask permission. Without unmask, masking always returns the masked value, so support staff can never see the raw PII requirement met. Statement 2 is no, and this is the trap in the question. A row-level security filter predicate silently removes rows from every query, and it keys off the suser sname function, the login name. There is no automatic exemption for sysadmin or database owner with filter predicates. An administrator running the application is filtered exactly like anyone else, unless the predicate function was deliberately written to let them through. Statement 3 is yes. Masking and row-level security work on different axes. Row-level security decides which rows you get. Masking decides how the columns look. They compose independently, so any row that survives the filter still comes back with its columns masked. Question 4, a drag and drop on the maintenance events requirement. You must complete an after update trigger so that last modified UTC refreshes whenever a row changes, while avoiding recursive updates. On screen, decide two things: the join condition between the base table and the inserted pseudo table and the where guard. You have 10 seconds. 2 blanks, 2 ideas. The join must connect each base row to its matching inserted row using the primary key. m.maintenanceID equals i.maintenanceID that guarantees the timestamp lands on exactly the rows that changed. Joining on vehicle ID would be wrong because one vehicle has many maintenance events, so you'd match the wrong rows. And i.maintenanceID is not null, is a filter, not a join. It can't correlate the two tables. The where guard is what prevents infinite recursion. An after update trigger that issues its own update will normally fire itself again. But by adding where m.last modified UTC is not equal to i.last modified UTC, the second pass finds the timestamps already match, so 0 rows qualify, the inner update changes nothing, and the cascade stops on its own. Question 5 on that slow dashboard. The query filters fleet vehicles by fleet ID and the plan shows a clustered index scan. It's reading the whole table. Recommend the fix. Review the 4 index options on screen. You have 10 seconds. The answer is B on fleet ID, a non-clustered index that includes last updated UTC, engine status, and battery health. Here's the mechanics. The plan scans because there's no useful index for the fleet ID filter. B fixes both halves. Fleet ID as the key column lets the optimizer seek straight to the matching rows, and the include list puts every column the select needs into the index, making it covering so there are no extra lookups back to the table. Scan becomes seek. Now the others. Option A. A table can have only one clustered index, and clustering on last updated UTC does nothing for a fleet ID quality filter and isn't covering. Option C. It leads on last updated UTC, so the index is ordered by the wrong column and can't seek on fleet ID. That's the leading column rule. Question 6. Pick 2 actions. The ingestion pipeline fails for 2 separate reasons: malformed JSON and duplicate payloads. Choose the 2 actions that resolve both. Review the 5 options on screen. You have 10 seconds. The answers are D and E, and notice each one targets one of the 2 failures. E handles malformed JSON. A check constraint that calls is JSON on the payload validates the structure at insert time, so bad JSON is rejected at the door instead of failing downstream. D handles duplicates. A unique index over a hash of the payload, for example a persisted hash bytes or checksum computed column, makes any repeated payload violate uniqueness and be rejected. Hashing is what makes comparing large documents cheap. Why not the rest? Snapshot isolation only changes how concurrent readers and writers see versions. It does nothing about bad or duplicate data. A trigger that rewrites malformed JSON is fragile and can silently corrupt data, and it still doesn't stop duplicates. Validate and reject is the right pattern, not autofix. And foreign keys enforce relationships between tables. They neither validate a JSON document nor detect a repeated payload. Question 7 on embeddings. Analysts can't find similar incidents by weather, traffic, or location. You must generate embeddings. Which column should you embed? Review the 4 columns on screen. You have 10 seconds. The answer is B, incident description. An embedding turns text into a vector that captures meaning, so it's only useful when the source column actually contains meaning, rich, natural language. The weather, traffic, and location details analysts care about are written in prose inside incident description, so embedding that field lets semantic search find incidents that are alike even when they don't share the exact same words. And it matches the requirement we read. Embeddings must be generated from rich natural language fields. The others don't qualify. Vehicle location is structured coordinates, no language to embed. Incident type is a small categorical label with a handful of fixed values, and embedding adds nothing over a simple filter. And severity score is a number, embedding it is meaningless. Only incident description carries the semantic signal. Question 8. You need low-latency similarity search over an embeddings column of type vector with 1536 dimensions. What do you include? Review the 4 options on screen. You have 10 seconds. The answer is D, a vector index on the vector column. Similarity search means finding the nearest vectors to a query vector. Doing that exactly means measuring the distance to every single row find for a few thousand rows, far too slow for low latency at scale. A vector index built on the DiskANN graph algorithm gives approximate nearest neighbor search. It walks a navigable graph instead of scanning everything, returning the closest matches in sublinear time with only a tiny accuracy trade-off. The others fail. A computed column that compares vectors row by row is the brute force exact scan, the very thing we're trying to avoid. A standard B-tree non-clustered index orders scalar values. It simply cannot index a high-dimensional vector type for nearest neighbor search. And a full-text index is for word and keyword lookup in text, not for distance between vectors. Question 9 on the development requirement. Developers in Visual Studio Code with GitHub Copilot must retrieve live database metadata. What do you recommend? Review the 4 options on screen. You have 10 seconds. The answer is C, use an MCP server. The keyword in the requirement is live. Copilot must reason over the database's current structure, not a copy of it. Model Context Protocol, MCP, lets a tool expose live capabilities to an AI client. The MS SQL MCP server connects to the actual database and streams up-to-the-minute metadata, tables, columns, procedures, relationships, to GitHub Copilot inside Visual Studio Code through its MS SQL chat participant. Every other option is a static snapshot. A DAC pack is a compiled copy of the schema at build time. The instant the database changes, it's stale. A Copilot instruction file is handwritten text nobody keeps perfectly in sync, and a database project in the repository is the source control definition. It reflects what was committed, not what's actually deployed and running right now. Static can't satisfy live. Only the MCP server is a live connection. And that completes case study 1, Contoso, all 9 questions. On screen is the full answer key. Every answer was independently verified against Microsoft Learn, question by question, so you can trust it going into your exam. If this depth of explanation helps you, subscribe. Next up is the Fabricam case study in the same format, full scenario first, then every question fully explained. See you there.